Hi, this is Dr. David Lubkeman, and this is a review for ECE 587 on solution of ordinary differential equations. In 587 class, we spent a lot of time working in the time domain as opposed to the phasor domain, and so what we need to do is we need to be able to both write and solve ordinary differential equations, and hopefully this is material you've seen before. Albeit maybe it was like 3 or 4 years ago when you're like a sophomore or junior in college. So we'll be working a number of different problems this semester, and we'll be kind of using this as a background. You'll actually see a number of different examples of how to apply it. But I just want to kind of start off with the review, and I'll post a few examples up on the Moodle site as well. So what I'm going to start with is reviewing the solution of first order equations using Laplace transforms. And I'm actually going to be using another technique called undetermined coefficients in class, but there's a lot of textbooks that would still use Laplace transforms, and so it would be kind of useful to know how to solve it both ways. And I'm going to go ahead and start with how we would solve these equations using Laplace transforms, and then I'm going to show you how the same type of problem could be solved using what we call the method of undetermined coefficients. And then I'll use this same undetermined coefficient method in order to solve a second order LC circuit. So for the Laplace transform approach, basically what you need to start with is you start with writing the differential equations in the time domain. And so for an example right here, we're going to take a look at a very simple RL circuit that's being driven by a DC source. And what you would do next is you go ahead and you take that differential equation, you convert that over into the Laplace transform domain. And you basically do that term by term. In order to see the formula solution, you have to manipulate this in the Laplace transform domain. And so there's quite a bit of manipulation, which isn't it's kind of the reason I don't really like to apply this technique. It gets kind of awkward, especially if you're solving sinusoidal circuits. But then once you have the terms manipulated properly, then you can take the inverse and get everything back into the time domain. And so the way this would work for this particular example is, let's suppose that this is being driven by a DC source. It's driven by a DC source. We have a resistance, we have an inductance in the circuit, and the switch closes at time equals 0. And you see a lot of the problems in this class will have a similar type of scenario where we're either closing or opening a switch. And so initially the circuit's de-energized. The current obviously going through this inductor is going to be 0, and when I close the switch, this is basically when the circuit's going to charge up. So if I write a Kirchhoff voltage law, basically the sum of the drops across the elements, Ri plus L di dt, this is going to be equal to the source voltage Vt, which in this case is going to be a DC constant value, say like a battery or DC supply. So Ri plus L di dt is going to be equal to VDC. And what we would do next is we would take each term in there and we would convert that over into the Laplace transform domain. And so I got to take the Laplace transform of all the terms on the left and also all the terms on the right. And when I convert the current in the time domain over in the Laplace domain, what I have instead of I as a function of t, I get I as a function of s. Now when I have a derivative, when I have a di dt term, what that transforms over into the Laplace domain is going to be s I as a function of s minus I 0, where that would be the current at time equal to 0. And then when you look on the right hand side, if I have a constant value, that's going to transform in the Laplace domain as that constant value divided by Is. Okay, so in this particular case, this initial condition is just going to be equal to 0. Because if I initially don't have any current going through that inductor because I have an open circuit, as soon as I close it, the current going through an inductor cannot change instantaneously, so the current right before the switch closes and right after the switch closes is going to be the same, is going to be equal to 0. Now, once I have everything converted over into the Laplace domain, then what I need to do is I need to start manipulating the equation so I can solve in terms of I sub s. All right, so I set everything up where I can solve in terms of I sub s. I'm going to go ahead and set this initial value for current equal to 0. And when I do this, I'm going to get this kind of a complicated expression where I've got two terms multiplied by each other. And the problem is that it's not really obvious from looking at that how I can kind of convert that back into the time domain. So what I have to do is I have to kind of break this into two parts. One where I have A over S, and the other one where I have B over S plus R over L. Because I know when I convert this back to the time domain, I'm going to have a constant value, and I'm going to have an exponential that's going to be to the power of the root of this term, S plus R over L. And so what I need to do in order to kind of keep moving forward is I need to solve for A and B. And this is where what you need to do is you need to apply what we call partial fraction expansion. So basically what I do is I take this first term, I multiply both the numerator and denominator by S plus R over L. For the second term, I'm going to multiply that by S over S. And the reason I'm doing this is I want to get the same denominator, S times S plus R over L, but what I want to do is I want to have everything broken down in the numerator in terms of the coefficients A and B, which is what I want to solve for. And once I've done this, then what I need to do is I need to find out what A and B are. Well, if I combine the terms associated with S, what I see I'm going to have A plus B times S. And if I go back to this original expression, I see should be no coefficients on the S terms in the numerator. That should be equal to 0. So what this means is that A plus B is equal to 0. As far as this constant term in the numerator, A times R over L, well, that particular term, that has to coincide with 1. And so A times R over L is equal to 1, and what I can do is I've got basically two equations and two unknowns, and I could use this for solving for A and B. So in this case, A is equal to L over R, B is equal to minus L over R. And when I substitute this in, I can kind of manipulate the terms around a little bit to get things into a little bit better form. And what I get is I sub S is going to be VDC over R times 1 over S minus 1 over S plus R over L. And so the reason we want to get into this form is to make it easier to convert back, to take the inverse Laplace in order to get back into the time domain. And we know whenever we have 1 over S, this is going to correspond to a constant value in the time domain. And so this VDC over R times 1 over S, this is going to translate back into the time domain as VDC over R. And then this term right here, this VDC over R times minus 1 over S plus R over L, well, basically that's going to kind of translate back into a term e to the st, where S is going to be the root of the equation S plus R over L equal to 0, where S is equal to minus R over L. And so the inverse Laplace of VDC minus 1 over S plus R over L is going to translate back into the time domain as minus VDC over R times e to the minus RL times t. And so what we see from here is we actually have two parts to this equation, or to this solution, I should say. There's a steady state part, which is the VDC over R, and there's a transit part, which is the minus VDC over R times e to the minus R over L times t. And so basically, for a sanity check, what we can do is we can go back to this circuit right here, and we know, like in steady state, that this inductor is basically going to map into a short circuit. If I have a DC circuit when everything kind of dies out when we get in a steady state, and the inductor looks like a short. So basically the current I'm going to have flowing is going to be VDC over R. Okay, so that's what I'm going to have in steady state, and that kind of corresponds to the first part of the solution right here. The second part corresponds to the transit, and basically what we're going to see here is at time equals 0, the first term and the second term cancel out, the current's equal to 0, which is we would expect. And basically what's going to happen is we're going to have basically an exponential change where that current's going to go from 0 to VDC over R. And so basically it kind of looks almost like the circuit's kind of charging the inductor up in a way. So anyway, this is how you would work this problem through if you're using Laplace transforms. And the reason I don't really like this approach, I mean, you could use this on your homeworks and exams if you want, but the reason I don't like this approach is you have to use this method of partial fraction expansion, and working in sinusoidal forcing functions like we do when we're working with 50 or 60 hertz. This is going to get kind of awkward because of the terms are going to be associated with sinusoids. And so I find it a lot easier to use this next method, which is this method of undetermined coefficients. And so this is going to make use of the property that when we're solving these equations, and let's suppose we're solving for y, where this could be a voltage or a current, basically what we're going to have when we solve these equations is we're going to have two parts to them. There's going to be the steady state part, and there's going to be the transit part. And so the steady state, sometimes this is referred to the particular solution. Sometimes this is going to refer to, this is referred to as the non-homogeneous solution. There'll be another transit part. This is sometimes referred to as a complementary solution. This is going to be also called the homogeneous solution. And from our standpoint, if we're working with sinusoidal sources, then basically this part of the solution, YSS, this would correspond to what we would compute if we use phasor analysis. So we already know how to do this. I mean, if we know how to do phasor analysis, you know how to get YSS already. But what we're trying to do in this class is we're trying to get this additional part, which is the transit portion of the solution. Okay, what basically happens between when, say, like a switching action occurs and we get into, like, say, like sinusoidal steady state. And so a lot of times we're kind of focused on, you know, what's this transit part. So this is the reason I kind of like this method of undetermined coefficients, because we can kind of leverage the fact we know we already have a lot of techniques for getting the steady state part. We just now have to kind of figure out, well, what's this additional transit part of the solution. So if we take the same example, we'll take the same RL type of a circuit, where we're closing the switch at time equal to 0. If you have a DC forcing function, you know that the form of the solution is going to kind of match the form of the source. If I had a sinusoidal forcing function in steady state, I'd have a sinusoidal as far as my solution. If I have a DC forcing function, the form of my solution is going to be a constant as well to kind of match that. So in this case, we know that the steady state current is going to be some type of a constant value, and for now we can just refer to this as A. And so if I have a differential equation I'm writing, Ri plus L di dt is equal to VDC, if I substitute into this differential equation for this value A, then what we're going to get is we're going to get Ri mapping to R times A, and then the derivative of this current with respect to time, this is just simply going to be equal to 0, so I can substitute this in, and I'm going to see that A is equal to VDC over R. And the steady state portion of this current is just simply going to be VDC over R. Now, if you want to go ahead and assume some sort of form of the current, that would be one way you can work this like I did right here. Probably the simplest way of actually getting to this, though, would be just to realize that if you have a DC forcing function, that in steady state your inductors look like shorts, your capacitors look like open circuits, and just go ahead and make that substitution and then solve for what the steady state current is. So if this inductance basically looked like a short right here, then you're going to have this basically VDC driving current through R in steady state, which is going to give us a steady state current of VDC over R. So however you want to get this is fine by me. Probably what I would probably more realistically do is just look at the circuit and just make the assumption that inductors look like shorts and capacitors look like open circuits and get this. But anyway, this shows you a couple different ways you can get to the steady state part. So what about the transit part now? Basically what the transit part is going to be what we get if we solve the homogeneous equation where we don't have any forcing function to the circuit, right? And so in this case, in the time domain, this would map to Ri plus L di dt is equal to 0. And the thing we need to keep in mind in this case is this transit portion. When we talk about I0, in this case for this transit portion, that's not the total current, it's just the current that's associated with the transit part. So that's not necessarily equal to 0. Now, if we were going to take this and convert this over in the Laplace domain, what we would see is we would have RIS plus LSIS minus LI0 equal to 0. And so if I wanted to solve this for IS again, what we would see is that IS would be LI0 over R plus S over L. And again, if I would convert this back, this would basically have something of the form of AE to the ST, where S is the root of this particular equation. All right. In other words, what we're solving for is we're solving for S such that R plus SL is equal to 0. And this expression right here, R plus SL, this is what we refer to a lot of times as a characteristic equation. So if I get the roots of that, basically what that does is it gives me the form of the response in the time domain. All right. Another way you could be thinking about this is if you had something of the form of Ri plus L di dt equal to 0, that everywhere you saw like a derivative, you just replace that by S. If you saw a second derivative, you replace that by S squared. So another way of getting to this would be you're going to have R plus, you see that derivative in there, S times L. That's all being multiplied by I sub S. And so anyway, if you want to come up with this characteristic equation, one simple way of doing that would just simply be take all the derivatives and just substitute by S. So in this case, the form of the characteristic equation is R plus S equals 0. The root is minus R over L. And then basically what we're going to have for the form of the solution is AEST, and if I substitute in there for the root, that's AE to the minus RL times T, right? So that's going to be the form of the transit. It's a decaying exponential. So the total solution is going to be the sum of the steady state part and the transit part. Okay, so IT is ISS plus I transit. The steady state part is just like this DC solution, VDC over R. The transit part is AE to the minus R over L times T. The next thing we need to do is we need to solve for the unknown, which in this case is A. And how are we going to get that? Well, we have to apply initial conditions associated with the switching action. So let's suppose in this particular circuit we've got the series inductor. Well, right before the switching occurs, that current going through the inductor is 0. Right after the switching action occurs, the inductor is going to resist any changes, so that means that these two currents have to be the same. And so for what we have for the boundary condition is the current at time equals 0 when the switching occurs is going to be equal to 0. So if I go back into this equation, what I can do is I can substitute in for time equals 0. E to the power of 0 is just simply going to be 1. And so I'm going to have VDC over R plus A is equal to 0. A is equal to minus VDC over R. And then finally I get the current is VDC over R minus VDC over R times E to the minus R over L times T for time greater than or equal to 0. If you want to really be picky about this, you should really say this is for time greater than or equal to 0, because actually for time less than 0 is just 0, right? So anyway, you can see that we get the same result, we get the same solution either way. But again, I think what you'll see if you kind of use this method of undetermined coefficients, where you go ahead and you break this into a steady state or transit part, you just kind of use what you know about solving AC and DC circuits to get the steady state part. You tack on the transit part, and then really what the work is figuring out what those coefficients are, and you get those by applying the boundary conditions. We're going to spend quite a bit of time also taking a look at solution to second order systems that have a combination of inductance and capacitance. And if you were going to excite this again by a DC source, where this switch is closed at time equals 0, then the boundary conditions you have associated with the capacitor is that that capacitor voltage cannot change instantaneously. So for inductor, it's the current that cannot change instantaneously. For capacitor, it's the voltage that cannot change instantaneously. And if you write an equation for this loop, you write like a Kirchhoff voltage law type of equation. The voltage across this inductor is LdIdt. The voltage across the capacitor is 1 over C times the integral of I, the current, times dt. For this particular case right here, I'm just going to ignore any sort of initial voltage across the capacitor, because that's not actually going to, it turns out it's not going to play into the solution anyway in this case. But anyway, these two voltages across the inductor capacitor, this is equal to V sub S, which in this case is a DC forcing function. Now, this form of the equation, this is something we may refer to as an integral differential equation. It's not really the form we want. So what I need to do is I need to take the derivative of both sides. And if I take the derivative of both sides, what we're going to see is that this term on the right is going to disappear. This is the constant value. This is just going to go to 0. And what I'm going to have is the inductance times the second derivative of the current with respect to time. And then the derivative cancels the integral, and I just simply get, for this particular term here, 1 over C times I. And so I get a second order differential equation. A lot of times we divide both sides by the inductance, and we get this very common form here. Second derivative of current with respect to time plus 1 over LC times I is equal to 0. So this is the equation that we need to solve in this case. So what's the characteristic equation? Well, again, what we would do is anytime I saw a first derivative, I would replace by s. If I saw a second derivative, I would replace by s squared. So we have s squared plus 1 over LC equal to 0 as a characteristic equation we need to solve the root for. In this case, what we're going to have, if I take the LC and move that on the opposite side of the equation, we're going to get a solution that's going to be imaginary. And so S in this case is going to be plus or minus J times 1 over the square root of LC, where we see this so often, we see this 1 over square root of LC or often, we're going to call this the natural or resonant frequency for this particular circuit. So S is equal to plus minus J times omega naught. All right, and just keep in mind, if you recall your properties of terms here, the J squared is going to correspond to minus 1. So anyway, we've got this particular solution right here for the characteristic equation, and now we need to figure out, well, what's the transit form of the current right here. So in this particular case, what we're going to have a solution of the form, since we have two roots, where we're going to have one term that's going to be e to the s1t. We're going to have another term that's going to be e to the s2 times t. We're going to have coefficients c1 and c2, and you see just a little bit why I'm not using a1 and a2. And when I plug in for s1, these powers on the exponentials, these are going to be complex numbers, e to the j omega naught t and minus j omega naught t. In order to kind of make sense out of this, since we typically don't work with these complex exponential terms, what we're going to do is we're going to convert this into sinusoid and cosine terms using what's called the Euler identity. And so Euler identity says that e to the power of j omega naught t, where this is a complex exponential, is equal to cosine omega naught t plus sine omega naught t. And you can kind of go through this on your own to see how this kind of maps over to a sinusoid. This is kind of a proof of this. But in the end, what you can do is you could take this expression for the current in terms of exponential terms, and you can convert this to the sum up to sine terms that are 9 degrees in quadrature with each other. So that transit current is going to map to a1 times cosine omega naught t plus a2 sine omega naught t, where omega naught's that natural ringing frequency. And you don't need to prove this each time you actually would use this. You just assume this is kind of a given when you're working these problems. So anyway, since I don't have any steady state current, since in this case for this DC forcing function the inductor would look like a short circuit, the capacitor would look like an open circuit, as time goes to infinity there wouldn't be any steady state current going through this particular circuit. Then when we get to this solution, we don't really have any steady state component to this is equal to 0. Then all we need to work with right here is we need to work with this transit portion of it. And so the current's going to be a1 cosine omega naught t plus a2 sine omega naught t, and we got to figure out now what a1 and a2 are. So we've got two initial conditions we're going to apply, and we're just going to do this one by one. For that series inductor in the circuit, since that current cannot change instantaneously, this initial value for current's equal to 0. All right, so time equals 0. We know this total current's equal to 0, right? In this particular case, if I plug in for time equal to 0, this cosine term, this is going to go to 1. This sine term is going to go to 0. And what this means is I at time equals 0 is just going to be equal to a1, which is equal to 0. So this means that a1 is equal to 0. So that term drops out. Where this gets a little bit more complicated is applying the second boundary condition. All right. So if you go back to that original circuit, you know that at time equals 0, that inductor voltage plus that capacitor voltage, that had to sum up to VDC. And we know also that the voltage at time equals 0 across that inductor is L di dt at time equals 0. All right, so we can substitute that into this particular equation, and that plus the capacitor voltage was equal to VDC. And what we can do now is we can use this to solve for the derivative of this current at time equals 0. And you'll see why we need this in just a little bit. So now if I solve for this derivative of current at time equals 0, we go back to basically this equation here. We see this is the same as VDC minus VC at time 0 divided by L. And now if I go back to the form of this solution, what I can do to get this expression for A2 is I can now take the derivative of both sides of this equation. And so when I do this, I'm going to get on the left hand side di dt. All right, I go to the right hand side, we know this first term disappears. I've just got the A2 sine omega naught t. The derivative of the sine omega naught t term is going to be omega naught times cosine omega naught t. Right? So what this is going to do It's going to give me A2 omega naught times cosine omega naught t. I evaluate this at time equals 0. This whole term right here is equal to 1. And then basically what I'm going to see is that A2 is going to be VDC minus VC at time 0 divided by omega naught times L. All right. So it takes a little bit more work in the case of second order systems in order to get the coefficients. So now I can make use of the fact that this is the expression for omega naught. I can go ahead and I can do some substitutions, and eventually I can find out that A2 is VDC minus V0 at time 0, VC at time 0, divided by the square root of L over C. And if I plug this in, I get the final solution for the current as shown here. Now, what do you see? What do you see as a result of this solution if I had a DC source and if I were to energize this inductance and this capacitance? And we're going to see this later on. I mean, this is going to be kind of what we're going to see when we have a power factor crushing capacitor switching in. This capacitor could have some initial voltage across it. All right, could have some initial voltage across it. And basically, the voltage across that switch, when that switch closes, is actually VDC minus VC0. All right. So basically, what we're going to have in the numerator term here is the voltage across that switch before it closes. It's going to be divided by the square root of L over C, which is going to have units of impedance. Okay, so this term is also referred to as a surge impedance or characteristic impedance, and basically that's going to be a function of the square root of L over C. So depending on the inductance and capacitance and their relative values, that's going to tend to determine whether we get a low current or high current. If we have a real low surge impedance, we get a really high value of current, and vice versa. And this current's going to oscillate at this natural frequency, which could actually be a pretty high value depending on what the values of L and C are. So anyway, we'll be doing a lot more of this during the semester. Primarily, we're going to be working on circuits where we have AC forcing functions instead of DC forcing functions. However, when we're talking about high frequency operation, sometimes we model the 60 Hertz as if it were a DC source and think, well, why? How can I do that? Well, let's suppose that the frequency of oscillation, that natural frequency, is somewhere around, say, like 10 kilohertz. Well, 10 kilohertz compared to 60 hertz almost makes the 60 hertz source almost look like it's DC, right? And so that's a common assumption you make when you're looking at these transits, is that sometimes you go ahead and just model the AC source even like it's DC if the transit ringing frequency is high enough. So anyway, if you want to do some additional reading on this, we've got some readings on reserve in the library. You can actually go to Greenwood's book, and he actually goes through this in chapter 1, 2, and 4. The thing about Greenwood's book, though, is he uses Laplace transforms to solve a lot of these, where I kind of use a different method. So at least you can take a look at the what you get for the solutions. There's another book by Schenkman that talks about doing transit analysis, and there's some material here in chapter 1. And if you also want to get some practice on solving different sort of problems, there's a Sham outline book which you can actually download. It's actually an ebook you can actually download. And they have one chapter on first order systems, and they have another chapter on second order and higher order systems. So if you just wanted to get some practice in doing these, this might be some different sources you might want to take a look at. But as we go through this semester, I'll be working these problems out in class, and so you can kind of see how they would be solved for all the different types of switching conditions. Okay, thank you.